6.4 Logarithmic Functions. Human senses, nearly all, work in a manner and obey Weber-Fetcher law that response of the sense machinery is logarithmic of an input. It is true at least for hearing, but also for eye sensitivity, temperature sense, etc., and of course in areas where it works normally. Because in extreme there are other processes such as pain, etc. So as in the case of hearing, what you experience is the logarithm of power of a sound wave by biological nature here sense construction. So it is natural to use logarithmic units. So basically when we feel things, hear things, our body is inputting that and processing it in the brain as a logarithm. So that's why we study them. The inverse of exponential functions are logarithmic functions. So I like to say they're same, but different. So they are inverses of each other. That's why all of chapter 6 is the way it is. It finally all comes together. We're talking about inverse functions. Logarithm and exponential are inverses of each other. So that's why we can change exponential statements to logarithmic statements and logarithmic statements to exponential statements. So the logarithmic function with base a, where a is greater than 0 and a cannot equal 1, is denoted by, so you read that as y is the logarithm with base a of x. You can just say y equals log ax. We know what you're talking about. So y equals logarithm with base a of x if and only if x equals a to the power of y. The domain of logarithmic function is y equals log base a of x is greater than 0. So these are the inverses of each other. Logarithms have a domain. We'll talk more about that in a couple examples. If we have special logarithms like ln or special exponents like e, that's how we're going to switch them. So y equals natural log x if and only if x equals e to the power of y. So when we're switching from exponent to logarithm and logarithm to exponent, to switch between the two, you're going to ask yourself these three questions. What's the given equation's base? What does the given equation equal? What's left over in the given equation? And we're just going to set it up in our template. So we're going to change each exponential statement to an equivalent statement involving a logarithm. So we're going to switch this to a log. So the first thing we're going to do is write log. Template, we have log base a of x. So we're going to start off with log. We're actually going to write it this way. We're going to write it that way. So we're going to start off with log and then fill in as we go. So we have log. The given base is 1.2. What does the given equal? The given equals m, so that's what we're going to write next. And then what's left over in the given? That's what's going to be your y. So in this case, it's 3. So that's our answer. We just switched it to a logarithm. We just found the inverse. All right, let's do the next one. So here it says e. So when we're talking about e, we're talking about ln. So if we have base e, that means ln. So we have ln. What does the given equal? It equals 9. And what's left over? b. All right, same thing. We're going to follow the template of log ax equals y. So we're going to write log first. What's the given base? We're given a as the base. What does the given equal? 24. What's left over that we haven't put? 4. No matter which way you go, you're going to ask yourself the same exact three questions. Let's change each logarithmic statement to an equivalent statement involving an exponent. So involving an exponent, we're talking about let's do it this way. A to the power of x equals y. So that's what we're going to fill out. So what's the given base? The little number is the base. We're given a. What does the given equal? Y. That's what's going to go as our exponent. Sorry, 5. I didn't mean to say y. It's 5. And then what's left over that we haven't messed with? 4. All right, let's do b. So we're putting it in this order. So we have log base e. So the base we're given is e. What does the given equal? It equals negative 3. What's left over that we haven't messed with? B. Equals B. Alright, C. So, what's the given base? 3. What does the given equal? C. What's left over? 5. That's why 6.3 or 4 seems like a lot of homework, because it's like 20 questions of you just doing stuff like this. So they're quick questions, but it's getting into that habit of doing it. With our calculator, we need to evaluate the expression. So we have ln 82 over 7 over 0.01. So I'm going to do it two ways with our calculator. So just in case, because I don't know what calculator you have. So I'll show you one way and then another. So the first thing we do, because the whole thing's a fraction, we're going to hit alpha, y equals, enter. And then a bar should come up. Then I'm going to put ln. So ln is right next to 4. So ln. Then I have another fraction. So alpha, y equals, enter. I'm going to put 82 over 7. And then on the bottom, we put 0.01. So you see how it looks exactly the way it looks on the page? We hit enter. And it says to round to 3 decimal places. So if we round this to 3 decimal places, we get 246.081. So that's one way to do it. Another way to do it with your calculator, we do it piece by piece. So ln, it's right next to 4, ln 82 divided by 7, hit enter, and then that is all divided by 0.01, and you see how we get the same exact thing. Alright, let's evaluate logarithmic expressions. So we're going to find the exact value of the logarithmic expression. Now, I don't know about you, but we don't know how to solve logarithms yet. We haven't learned that. So we do know something, though. We do know that they have to do with exponents. So what we're going to do is, when you can't solve as a log, switch to exponent. So we're going to switch log base 2 of 16 to an exponent. Now in here, because we're talking about an exponent, we need it to equal something, so we make it equal y. We're allowed to do that. We're totally allowed to do that. So let's switch this to an exponent. The given base is 2. What it equals, the given equals, is y. What's left over is 16. We know how to solve exponents. That's why we switch it, because we actually know how to do this. So we want the same base. So we want to leave it as 2, so 2 to the power of y. And then 16, that's 2 to the power of 4. That's 16. So we get rid of our bases, and we have y equals 4. So our final answer, we actually have to plug it back in. We have log base 2 of 16 equals 4. Alright, so we have log base 3 of 1 over 27 equals y. So we can't solve that exponent. So we're going to switch it to I just realized I spelled that wrong. We're going to switch it to a exponent, because we don't know how to solve logs. So if we can't solve logs, we switch it to an exponent. So the given base is 3. The given equals y. What's left over is 1 over 27. So remember that we're not allowed to have fractions with this, so we're going to flip it. We need to flip this and make it normal, because remember, if we have x to the power of negative 1, that's 1 over x. So we're going to do the same thing here. So we have 3 to the power of y equals 27 to the power of negative 1. Because you can go back and forth. So now we need it to be the same base. So it's already 3. Leave it as 3. So we have 3 to the power of y equals. So 27, that's 3 cubed. That's 27. But on top, we still have this negative 1. So now that we have the same bases, we can get rid of them. So we have y equals 3 times negative 1, which is just negative 3. So let's put it back. We have log base 3 of 1 over 27 equals negative 3. Your answer should be negative. It should be negative. Get different color. It should be negative because of the fraction. So it should be negative because our answer is a fraction. And in order to get a fraction out of an exponent, right, it needs to be negative. All right, let's determine the domain of the logarithmic function. The domain of a logarithmic function consists of the positive real numbers, so the argument of a logarithmic function must be greater than 0. So, argument, that's a new word for math. The argument is the parentheses, anything that's in a parenthesis or a absolute value. So that's the argument. You can have multiple arguments. You could have 1, 2, 3, 4, 5. You could have multiple arguments. So it's stating the argument must be greater than 0. So that's how we find the domain, is just set the argument greater than 0. The reason being because this, what we're given, that's the equal part. That's the log base, sorry, wrong one. A to the power of y equals x. That's that part right there. So we know that exponents never equal a negative number. So since exponents never equal a negative number, we have to know what makes the argument greater than 0. So that's what we're going to do. For part A, we're going to set the argument greater than 0. So x plus 3 is greater than 0. So we have to have x is greater than negative 3. So we can write our answer as x such that x is greater than negative 3. Or we can write it in interval notation, negative infinity, negative 3, union, negative 3 to infinity. All right, let's do B. So B, we have 2 arguments because we have 2 pieces inside the argument. So we have 1 plus x is greater than 0 and 1 minus x is greater than 0. So here we have x is greater than negative 1, and here we have 1 is greater than x. So in set notation, how do we know to put this in, how do I put this in set notation or interval notation? Well, first let's do interval notation. So I'm going to draw my x-axis, and on my x-axis I have 2 things, negative 1 and positive 1. So for negative 1, it says it's greater than, so it goes this way. For positive 1, if we rewrite this, that is x is less than 1, so it goes to the left. You see how it goes together? Since it goes together, this is a compound inequality. So since this is a compound, we're going to write our answers in set notation this way. So we have x such that smallest number is negative 1, and then less than x, less than bigger number. When it's compound, it's always going to be less than, less than. Only when it's compound. Since it goes together, that's compound. For interval notation, since these go together, it'll be negative 1 to 1. When it's compound, it always is number, number. All right, C. So C, our argument is an absolute value. So the argument is an absolute value. We know something special about absolute values. Absolute values always produce positive numbers, so it will never be negative. No matter what, you can never put anything in there and have it become negative because it always turns to positive. So if the rule is for logarithms that the domain, the argument has to be greater than 0, isn't it no matter what we plug in, it'll just be greater than 0 no matter what? Except the only thing we can't plug in is 0. Because if we plug in 0, right, it becomes 0. So the only thing that it can't be is 0. Because I can plug in any number. I can plug in any number into the absolute value, and it's always going to be positive, except 0, because 0 is 0. But the argument has to be greater than 0. So it cannot be 0. So in set notation, it would be x such that x cannot be 0. And in interval notation, it would be negative infinity 0, union 0 to infinity. Now we're going to solve logarithmic equations. So we're going to solve log base 3 of 4x minus 7 equals 2. So there's just 2 steps we need to do here. That's it, just 2. I'm going to write them down for us. The first step is we're going to switch log to exponent. That's what we're going to do, switch log to exponent. Our second step, after we solve for it, so I guess switch log to exponent, solve. And then our second step is to find and check the domain. Because we're trying to solve logarithms, and remember, logarithms have a domain because we're not allowed to have negative numbers with exponents. It always turns into positive. When it equals, it's going to be a positive number. So let's switch this to an exponent. We have the given base is 3. The given equation equals 2, and what's left over is 4x minus 7. I can simplify 3 squared, I know that's 9. And now we can solve this, so we're going to add 7 over. And when we do, we have 16 equals 4x, divide by 4. So 4 is possibly x, but don't forget, we need to check the domain. We need to check that domain. So let's find our domain. So remember, the domain is argument is greater than 0. So 4x minus 7 is greater than 0. So we have 4x is greater than 7. Divide by 4. So we have x is greater than 7 over 4. Now, 7 over 4, I don't know what number that is. It's 1.75. So what we need to do is check to see if 4 fits in there. Is 4 greater than or greater than 1.75? Yes, that's true. Since that is a true statement, our answer is just 4. We have to put them in braces because it's a set. It's a solution set. All right, let's do the other one. So the first thing we're going to do is switch it to a logarithm. So the given base is x. What the given is equal is squared, so 2, and what's left over is 64. So let's solve for x. We're going to solve for x by square rooting. So we have x equals positive negative 8. Now we have to find the domain. So remember, the argument is the thing with the variable. So the thing with the variable here is x. So we have to do x is greater than 0. That is the domain. So now we have to check it for both because we have x is possibly negative 8 and x is possibly positive 8. So let's check them. So we're going to check our first one. We have negative 8 greater than 0. That is false. Since that is false, negative 8 is not an answer. Let's check positive 8. So we're going to check positive 8. So positive 8 is greater than 0. That's true. Since that is a true statement, the only solution we have is 8. We're going to use logarithms to solve an exponential equation. So how do we know to switch it? Well, e to the power of 2x equals 5, isn't this where we find the same base? But 5 and e can never have the same base. Since that's the case and we can't solve it, so if you can't solve as an exponent, switch it to log. So let's do that. So the given base is e, which means ln. E and ln always go together. What's given is the exponent of 5, or sorry, what's given is 5, and what's left over is 2x. We can solve for x now. We can solve for x by dividing each side by 2. So we have ln, I'm going to bring it over here. We have ln 5 over 2 equals x. That is our exact answer. Plug it into your calculator, that'll give you the approximate. So if you plug it into your calculator, you get 0.8047, and that is our approximate answer. All right, let's solve the equation right in terms of the common logarithm. Don't worry about what that means, let's just solve it. So, first things first, I want to try to see if I can solve this as is. So we have 4 times 10 to the power of 9 minus x equals 15. Now, why'd they write it this way? Why'd they write it that way? Why not just have it be 40? Because it's very different. Because that's 10 to the power of 9 minus x, and whatever that is, then we multiply by 4. So 40 to the power of 9 minus x is very different. So let's get rid of that 4 because it just shouldn't be there to begin with. So we're going to divide each side by 4. So we have 10 to the power of 9 minus x equals 15 over 4. Now, we can never get the same base. 10 and 15 over 4 can never have the same base. Since they can never be the same base, let's switch this to logarithm. So we have log. The given base is 10. The given equals 15 over 4. And what's left over is 9 minus x. All we need to do is just solve the equation, meaning get x by itself. So I'm going to subtract 9 to both sides. And when we do, we have log base 10 of 15 over 4 minus 9 equals negative x. We're not allowed to have negative x, so I'm going to divide or multiply by negative 1. So now we have negative log base 10, 15 over 4 plus 9 equals x, because we have to distribute the negative. Write in terms of the common logarithm. Common logarithm is log base 10, or if it just says log. That's log base 10. The button on your calculator that says log is log base 10. So we can plug this into our calculator. So this would be our exact answer. To get the approximate, we're going to plug it into our calculator. So we're only allowed to plug it in when it's base 10. So we have negative log. Log is base 10. So that log button is only when it's 10. 15 over 4. So alpha y equals enter 15 over 4 plus 9. So we get our approximate is about 8.426. If you have an older calculator, I'll show you another way. So negative log 15 divided by 4, enter, and then you add 9. Alright, last example. Blood alcohol concentration, BAC, is the measure of amount of alcohol in a person's bloodstream. A BAC of 0.04 means that a person has 4 parts alcohol per 10,000 parts blood in the body. Relative risk is defined as the likelihood of one event occurring divided by the likelihood of a second event occurring. For example, if an individual with a BAC of 0.02 is 1.4 times as likely to have a car accident as an individual who has not been drinking, the relative risk of an accident with BAC of 0.02% is 1.4. Recent medical research suggests that the relative risk of R of having an accident while driving a car can be modeled by the equation of the form R equals e to the power of kx, where x is the percentage of concentration of alcohol in the bloodstream and k is a constant. So before I even read any A, B, C, D, I'm going to pull out what it's telling me. Okay, it gave me a formula. R equals e to the power of kx. It tells me R is risk. And remember, E, it just represents a number like pi. It's 2.71, but you don't need to know that. There's an E button on your calculator. Then it tells me K is the constant. K is always your constant. And then it tells X is your BAC. So part A, research indicates that the relative risk of a person having an accident with BAC of 0.02% is 1.4. Find the constant K in the equation. So in part A, it tells us that research tells us that relative risk of a person with BAC, so BAC of 0.02. So we're given BAC equals 0.02. And the risk is 1.4. So risk is 1.4. We need to find the constant. So we have 1.4 equals e to the power of k, that's what we're trying to find, times x, which is our BAC of 0.02. Anytime we see e and an equal sign like this, we're going to switch it to a logarithm. So we're going to switch this to ln. So we have ln, that's the given base. The given equals 1.4. And it equals what's left over. So what's left over is technically 0.02k. So we need to solve for k. So I'm going to divide by 0.02. So we have ln 1.4 over 0.02 equals our constant. With our calculator, our constant is about 16.82. How did I know to do 2 decimal places? Because we're given 2 decimal places. That's how I knew to go with 2 decimal places. Alright, we found our constant. That was part A. Part B, using this value of k, what is the relative risk if the concentration is 0.17%? So part B is asking, what's the risk? So what is the risk if your BAC, your concentration, is 0.17? And it says to use the constant we found, use the value we found. So the k we found was 16.82. So we're going to plug it into r equals e to the power of kx. So r, we don't know it, we're trying to find it, equals e to the power of k, which is 16.82, times x, which is your BAC of 0.17, So with your calculator, just plug this in exactly how it looks. Remember, E is second divide. So if you want to get E on your calculator, press second divide. So plug that in exactly the way it looks. When we plug it in exactly the way it looks, we get second divide to the power of 16.82 times 0.17, and we get 17.45. So the risk is 17.451, so on, but you see how the risk, they just give us one decimal point for the risk, so we have risk equals 17.5. So what we just found, what did we just find? So with a BAC of 0.17%, the person is 17.5 times as likely to have a car accident as a person with no BAC. 0.17, you are way over the limit. 0.08 is the limit. So 0.17, that's just ridiculous. But it makes sense that you're 17 times more likely to get into an accident. Alright, part C. Using the same value of k with BAC corresponding, what BAC corresponds to a relative risk of 100? Alrighty, part C. So, using the same value of k, that's the same value we already have, what BAC corresponds to a risk of 100? So we're given risk is 100. We need to find what BAC, which is x, and then we're using the same constant of 16.82. So let's go ahead and plug it in. We have risk, which is 100. Alrighty, part C, we're going to plug everything in. So we have r, which is 100, equals e to the power of kx, so 16.82 times x, which we don't know, that's what we're trying to find. So anytime we have e and we're trying to solve for a variable, we're going to switch this to ln. So we have ln, that's the base, what's given, what it equals is 100, and what's left over is 16.82x. So now we're going to divide by 16.82. When you use your calculator, you get 0.27 equals x. So what we just found with a BAC of 0.27%, the risk is 100. So they deemed that after around 0.27% of drinking, that you are going to have, you're going to get into a car accident no matter what. No matter what, you are going to crash your car, because that's how impaired you are. Part D. So part D, if law asserts that anyone with a risk of 4 or more should not have driving privileges, at what concentration of alcohol in the bloodstream should a driver be arrested and charged with a DUI, driving under the influence? So we're given The relative risk is 4. And then we're trying to find what concentration. So we're still going to be using the same constant. That's not going to change. That's why it's called the constant. So we're still using our constant. We're given the risk is 4. And then we want to find the BAC. We want to find that. So let's plug it into our little equation. We have R, which is 4, equals e to the power of k, which is 16.82 times x. So just like before, anytime we're trying to solve for a variable with e, we're going to switch this to ln. So we have ln 4 equals 16.82x. We're going to divide to get it by itself. And when we divide, we get 0.08 equals x. And we round to 2 decimal places because they're giving us blood alcohol content 2 decimal places. So what this means a driver with a BAC of 0.08% or more should be arrested for a DUI. And guess what? That's the legal limit. So if you were under that limit, like say 0.06, you're still at a risk of getting into a car accident, but you're still able to legally drive. Doesn't mean you should. Does not mean you should.